Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
First, I want to welcome Mark Abbott, who's the Dean of the College of Oceanographic and Atmospheric Sciences at Oregon State. And so, Mark.
Thanks, Dan. And just to, it's always odd when somebody says, "What's a dean doing up here?" Sorry, Dean. Luckily, my first name is not Dean, or I'd be known as Dean. But anyway, I brought Ganesh Gopalan, who's over here, and Chuck Sears. They've really done a lot of the work. And Ganesh has presented some of this work at earlier eScience meetings, but I'm going to just kind of update where you are, where we are today. Those of you who remember your English literature, The Rime of the Ancient Mariner, Coleridge, data everywhere. Well, actually, he said water everywhere, or referring to the ocean. But we still have this issue of just volumes of data, and we'll talk about also the complexities of data, and how do we find the things of interest. And in some sense, this, it really is something old and something new. We've seen this, and you go through the fourth paradigm, the volumes of data, the usual suspects, as I say, which is the growth in the volume and the growth in variety, and we all tear our look at the Fry's ad in the Oakland Tribune today, and you see a terabyte drive for $60, and you say, well, gee, I remember when that was a big expensive problem. So, we still have these usual problems, but Moore's law keeps affecting everything, not only, the speed of processors, but now in terms of the complexity and the tasks that you can get on a single chip, and then you can extend that to looking at the storage of data, etc. It really, Moore's law does more than just speed things up. It disrupts life. And so we can say, well, now data centers can just store more data, but just think about what that does out at the edges. Our old workflows of things that are really pretty much a mechanical, as I say, mechanical process. You saw some of that in Phil Bourne's talk. I'll go through some of that. But we have a whole range of what I would call the new suspects that are out there. Much more emphasis on real time, both models and observing networks, much more smarts of data and intelligence out at the edges of this network. And I think for 25 years, we've really wrestled with the old models and not recognized that the PC did change everything. And now when you start adding this into sensor networks and the rest, you have to start thinking about different types of workflows where things aren't as predictable. And things are changing all the time as people see things and reconfigure sensors based on the environment that they're observing. And you get this kind of unpredictability. But we still wrestle with the problem with program managers and congressional staffers saying, but you're collecting all this data in earth science, but you only look at 1 to 5% of it. Why don't you just collect the 1 to 5% that you know you need? Well, that would be good, but that would be called commodity processing because that's not science. There's that innovation that we need to have, and I think that's why we've really enjoyed working the last several years with Dan Fay and his group at Microsoft Research, because they really are trying to say, what are the tools I can bring to an individual scientist, student, or public official to work with that data to bring the individual into that data set. Well, I'm going to talk about a little bit about oceanography. Since I'm an oceanographer, now I'm an administrator, but I administer oceanographers, so I guess that counts. We had these sort of romantic ways of collecting data. We go to sea in ships. This is the Wacoma in Newport, Oregon. That's the OSU ship on a nice moonlit night. And sometimes life isn't so pleasant. You have the kind of rough environment that you have to deal with, and so people collect data, and they struggle to get those bits. These data are maybe large in volume, but quite valuable because people, really in some sense, it's not a whole lot of fun out there. But the interesting thing is that we had a relatively well-defined workflow, and in fact, several of these talks over the last 24 hours we've seen have kind of put this up. I've kind of put it a little bit differently. You can kind of break into this cycle at any spot, where you deploy some sort of measurement system, We get it back. We hope it worked. Not always. So in some sense, there's input arrows of both money and luck at times. We analyze the data. We write it up. We put the paper out. We hope it gets positive reviews. It gets published. Then we use that to write. Hope we can get more money. Go buy a new package, deploy, repeat. Sort of like your, shampoo, lather, rinse, repeat. That's this very nice system, and it's worked for many, many years, and it will continue to work for a long time. I mean, that's really at the core of the sort of process, particularly in earth science, where it's not a lab experiment. I can't control the ocean and manipulate a little bit. I really am collecting lots of data and looking to tease out complex relationships, that unpredictability side of it. But this kind of process, particularly you saw in Adam's talk last night, is changing in the sense that we're now driven by more collaboration. We have to bring more people into this process. They're interdisciplinary. They're not just getting biological and chemical and physical oceanographers to talk together. You have to get fisheries scientists together, or people who understand policy. And so you now begin to run into conflicts that appear in terms of language and culture. Everybody's bringing a sort of a different background into this well-defined workflow. And then when you look at the National Science Foundation, they say, oh, and by the way, this great science, we want to see broader impacts. And now, beginning in January next year, we want to see a 2-page data plan and how you're going to distribute that data. So what we've done is take this well-defined process and seriously fuzzed it up. Along with that workflow, and Dozier should probably remember what this is. This looks like a very well-defined data flow. You collect data, you have searches, data servers. It was even written with sort of in clouds. This is the EOS disk core system from 25 years ago. It looks a lot like what we do today and what we talk about doing today. We're advertising and distributed searches and et cetera. So what we're seeing, along with this change in the workflow and the kinds of change on the science demand in the data flows, because these things now live in your hand, in your sensor, or in your lab, or wherever. So how does that begin to change this whole process? And so one of the examples, this is some examples to begin to drill down into what we've been working with, is part of what NSF calls its Ocean Observatories Initiative. It's a drawing from John Delaney at the University of Washington. This is part of NSF's major research equipment facilities construction. Roughly $360 million is going to deploy a whole series of real always connected, always on sensors, some that are connected via cable, some that are going to come up to the surface and talk via satellite. This is just looking what's off the Oregon-Washington coast. So there's looking at plate processes off the Juan de Fuca plate, and then some coastal processes in this area here that OSU is leading. But you can see a whole range of sensors. It's not just going to sea, collecting water, putting sensors out, adaptive sensors they're on all the time. And what John likes to do in particular is to look at high-definition pictures. He's, in this case, looking at El Guapo, known as the Handsome One, a vent structure off Oregon, or the Washington coast, and trying to understand the biology associated with these types of features. And he said, it's nice. He gets pictures. He uses ROVs, remote-operated vehicles. But really what he wants to do is to tie into this fiber optic cable that's going to be out there, connected to the internet with power. And he said, it's nice to have a high-def camera out there. But John, being John, any of you who know him, said, but I want to go now stereo. I want 3D. So you start to think about the data volumes, and you say, well, why does he need to do that? Because in earth science, we don't know what we're going to see. There aren't controlled experiments you can run in this environment. Things happen, and you're 99% of the time not there when that thing happens. Real-time, always connected is going to revolutionize ocean sciences. We're used to going out, being at sea for 4 weeks, collecting data, bringing it back, putting it into that mechanical workflow, those normal data flows. This is going to completely disrupt it. This is an example where Moore's Law has really disrupted the way we do our science. So we get these new workflows. That these sensors aren't just passive collectors. They become autonomous. They become cooperating networks with each other, and they respond to the environment and change their behaviors. That's one part. The other part is we now are always connected to scientists and others. We have this mandate from NSF for outreach engagement. So these new capabilities really are breaking this sort of very predictable process apart. And we need, because of the volumes and this sort of autonomous that we want to get to, pushed out to the edges. Not only the edges of the sensors and the collection devices, but the people as well. You've got to figure, how do I take that advantage of that smarts and intelligence that are out at the edges of the networks? How do I move to not just a sense network, but a response network? How do I build these new levels of collaboration? And I think that's really a balance issue. And that's a hard problem to do because we tend to like to think, let's go back to that EOS-DIS architecture of the cloud. But what does it mean to put things out at the edge? Moving things to the cloud for you business people, it really becomes a CapEx and an OpEx problem. What does that mean? Capital expense versus operating expense. Sometimes it makes sense from a business perspective to do things in the cloud, but in science, does that make sense? How do we handle that? So it's not just a simple matter of scaling up, which is really what we've done with Moore's Law for the last 20 years. Bigger, faster, better. We're doing more and different. It's a scaling out problem that we're really talking about. Different types of capabilities, different sorts of missions, and different sorts of tools. And that really breaks apart the workflow. So we're going to talk a little bit about one particular example, which are smart HD video data streams. Talk about how do we begin to put some of that out at the edge rather than bring all of that in. Can we look at this sort of real-time as well as retrospective search side? I should point out that in our lab at OSU, we have our own little sensor web. This is a digital red camera. Those of you who know, these are kind of becoming this standard in the Hollywood film industry. Just to give you a sense, 18 megabytes per frame, 30 frames a second. So you're getting a terabyte in tens of minutes, and there's half a terabyte of storage. That used to be out in the cloud in a big data center. Now it's in a lab, 1 PI. It's not that hard to do. And you can say, oh, well, that's good. Now I've just got 10,000 of these little data centers. That starts to change the nature of the workflow. Let me just show you an example of what these HD video streams look like. This is from a vent field off the Washington coast that John Delaney sent us. And unfortunately, it's a little bright in here, but you can sort of see some of the, maybe we probably don't want to turn the lights down. Everybody fall asleep. Yeah, why don't you do that? Because this goes on for a few minutes, Rob. We've got plenty of time. It's actually pretty cool stuff. Can't film in the dark. Okay. Well, you can sort of see some of the hot water coming out of here, out of these. You say, well, is that a biological structure? That's actually a geologic sulfide structure in here. The biology is all over in here. And what Delaney says, well, it's nice, but I don't want to park a graduate student in front of those videos. I really want to be able to say, when does something change? When is there an unexpected event? And that's really the nature of the scientific question that John and others want to look like. How do I turn these HD video streams into a scientific asset rather than a Cousteau documentary on Discovery Channel, which is good, but you can see this can be repurposed for multiple sources. You could use it to guide those sensors that are around that area. You see an event, can you trigger a sensor web to change its behavior? Can you use it for outreach and education? Do you bring all of that back, and how much do you do out at the edges versus centrally? Oops, sorry. So just to bring you up to speed, this is stuff that Ganesh has presented before, but what we've been using is the MPEG-7 descriptors to use a way to go through that video automatically rather than have somebody manually annotate and sort of begin to categorize that, store those endpoints in a SQL Server backend, and then use that to go out and find clips of interest that have features that we're looking at or interested in. Ganesh has done that a lot in looking at this sort of retrospective search, so you can build up these frames, sort of film clips, to say, you know, I'm interested in what's going on with tube worms, for example. And so I have all out of the hours of film, I can use the MPEG-7 descriptors to identify when the camera is seeing tube worms and when it's not, and just store those clips. But now he's also going to the point, can I begin to look for events that occur? And so that's the kind of where we are today, is beginning to look at these event descriptors to do that detection. And then the next step would be, can I trigger actions within this sensor web that I'm beginning to build? Well, one of the challenges that we've seen is, you know, going through video clips, we could do, you know, the mouse and the keyboard and enter and everything. And the other part now is saying, are there different kinds of interface tools that make it easier for people to find things? So, for example, you know, here's some tube worm scenes, some other clips, and we might say, I really want to find all the clips that sort of look like this. And rather than just have to type that in, we've been started with the HP TouchSmart shell to look at sort of a multi-touch interface, use the Windows Presentation Foundation to build that, and we just basically say, you know, I've got a clip here that is like this, now go show me all the ones that look like that. That query then goes out to the SQL Server, comes back, and we get a gallery. Then it says, okay, I'm interested in features that look like this, and here are all the video clips that have something that sort of from the MPEG-7 criteria match that fairly well. And so what's nice about that is that now this is all done in a touch mode. So for resizing clips, moving things around, minimizing the gallery, scrolling through becomes a lot easier and more natural process to work through. And so that interface in the MPEG-7, then we can take that knowledge that we've captured, and then we're beginning to look at storing that within a pivot collection. So we started looking at some of the best video clips that we've seen, and then we use pivot to do the actual navigation and browsing through the clips. So the integration right now, it becomes kind of a bit of a problem. It's science data. You know, we've got sort of some of the basic characteristics. You know, we can go and look at some of these, but a lot of these become sort of unique. It has tube worms or it has sulfide structures. And so what we're looking at for the next round is getting some of the actual environmental data that's collected along with the video and using that to say, you know, show me all the tube worms where the temperature is above some threshold. What we also find is that the multi-touch way is a really great way to go through these masses of video clips and find things in a it's just a better way to do things than trying the traditional database. The Windows Foundations are a great way to implement that, and Pivot looks like a nice way to capture and navigate through that. But let's circle back to the beginning. So what we've found is that the access to these big data sets is really changing how we want to work with things. We don't want to do this in a centralized archive. What we find is that this video data, and there are going to be many others, is so rich, and the potential range of applications and services is so rich, you can't take the usual standards and committees and say, here's the ontology, here are the semantics, here's how everything's going to be done. Well, in a lot of fields, but within earth science, I don't think we're there yet. We've done a lot of that work, and what we find is it depends on the question you're asking. So I end up repeating it all the time, over and over. Had this argument with Dozier 25 years ago on SQL databases. Nobody could agree on what was the appropriate metadata. Well, on some level, yes, you can. You can say where you can find things. But it tends to be the production and the least interesting thing. It's not the innovative part of it. And so what we're looking at is we know that the scaling up is hard. Big data always presents challenges, but it's the scaling out. It's the handling of the different missions. And now when I start saying, I need these data to make decisions, either how to control a sensor or which wetlands to rehabilitate, becomes a really hard process, particularly in the earth science. We also found these things like MPEG-7. Don't expect you can automate everything. We all know that. But a smoke detector is a good thing. It may not tell you that, well, you're just broiling chicken and it's burning the skin, or did you leave the pan on the burner and forget and it's now melting. It will tell you the difference. It just says, there's smoke here. You might want to take a look. And so we're looking at this approach as sort of getting at the 70 to 80% level. The next thing that we would like to do is to think about how can you begin to do this kind of tagging, this kind of finding features of interest in a much more of a networked approach. In some sense, bringing in, as I will call it, the power of the crowd, of people thinking about, how can they share what they find of interest? And I think that's going to be the interesting thing. If people are doing things out at the edges, people are their own little data centers with their own sets of network services, how can I begin to aggregate that together? And I think that's going to be the sort of new model of collaboration and publication. That leads to that last bullet, which is we're seeing a whole range of different types of sources and different types of people working with the data. I think that that's probably the biggest change, and we might think, well, standards and committees are good for setting up some levels of metadata, but a lot of it's going to be done on the fly. You're going to recompute things all the time, over and over again. It starts to get to this sort of restructuring the data sets based on the usage and supply and doing that in real time. Shoshani at Lawrence Berkeley Lab 15, 20 years ago talked about looking at database patterns, looking at the usage, and then restructuring the database based on that. I think we've got enough computational power to do that in real time. And I think that begins to change the nature of the workflow and how we do things. Don't underestimate. Scientists are an incredibly conservative batch. It's nice to hear Adam say and Phil say, well, the young scientists are going to do things if only the old folks will let them do it. It's hard. The reward structure is pretty ingrained, and I think the resistance to doing things in new ways of sharing and collaborating is going to be a hard thing. And you need to think about the overall system, not just where we are today and the tools we have today, because the world's going to be changing. And then our sort of last up, a separate type of slide is we do think this whole natural user interface is going to be a different way of how we interact with our data and interact with each other. And I think there are a lot of questions on what's the right one, where can it add value, and I think, again, it brings in a lot of different teams together, particularly within the Microsoft world. We've done a little bit of work with the Surface. That wasn't as easy as one might think. But clearly there are interesting potentials of linking with the gaming folks, some of the new technologies that some of us saw at the Faculty Summit, bridging that gap between science and gaming. Because when you start to think about it, it's almost that's the metaphor that we're talking about. We're all working on a system that we're trying to understand the rules and collaborating with each other. It looks like a network game. And that sort of new user experience that's highly distributed is going to be sort of the next challenge. And so just last acknowledgments, and I'll take some questions from folks.
I don't know if I missed, but do you have any intention of annotating the videos to help retrieve relevant information?
Right. Yeah, we're annotating right now, but only using the MPEG-7 descriptors. But one could think about other types of ways of doing that, either manual or what have you.
Yeah, that was my
Right now, the traditional way is a poor young undergraduate student sits there. I see a fish. That's not the best way to do things.
Hi.
Yeah.
Nice talk. Great.
Thank you.
Lots of good ideas. So a fundamental question that arises in these sensor nets or responded nets, as you nicely put it, is how do you get the data to drive computing? Often, if you're doing analysis and you have, let's say, strong bounds on the time to respond with the analysis, which in turn helps you or determines how you respond. So you didn't, maybe I missed something, you didn't dwell deeply on that, but are there some general programming systems approaches? Because that's something which is so common across a large variety of problems.
Yeah, it's a great problem. We're starting, in the ocean community, just starting to scratch the surface. I think one of the issues, for example, you put out these gliders that are collecting data. And you can begin to couple that data into assimilation models that predict circulation. And they're saying, well, can I use that to drive where I need to do better sampling? It's still there. It's very much in its infancy stage. But I'm not sure that we're even there to say what the programming model should be. Because there become some interesting questions about, well, what are you trying to minimize? I mean, you've got to think about the error and errors both in sampling and understanding of the processes. And there aren't any standard criteria or approaches, but it's a great question. We've got 25 years with this bit of infrastructure out there to begin to answer that one. It's a question way in the back.
So, as a graduate student, I appreciate that you pushed the fish annotations out of the but you kind of touched on a few things here, and I'm wondering what you think about taking this massive data flow and kind of pushing it out to the citizen scientists. There are lots of armchair oceanographers out there who would love to kind of be a part of this, particularly if they can get some kind of
I think
recognition of it.
That's exactly, I mean, these data, no proprietary period, they're real time, they're out there all the time. That's the plan. NSF insists on that. The question is, how can you begin to harness it? That's what I was thinking. Somebody else, a million eyes looking at something is a lot better than just a couple of graduate students in a lab. I don't think we've figured out the structure to do that, but the fact of the matter is there's going to be a lot of compute power and time out at the edges. And how to marshal those forces is going to be a really interesting challenge. It's a great question.
Great. Thanks, Mark. And we'll get on time. Next up, Alex Szalay from Johns Hopkins to talk about the extreme database-centric scientific computing, some of the work they've been doing for a while there.
Thank you very much. So when we look at how scientific data analysis is done today, it is clear that the data still keeps growing, roughly doubling every year. And we are crossing over now from hundreds of terabytes that is coming in different scientific disciplines to petabytes. And the other challenge is that the data is everywhere. It's usually tied to the experimental facilities. So the data is, for example, if we have a telescope or a radio telescope, typically the archive is, if not right at the telescope, but it is still associated with the group who are collecting the data, and it is residing there. And there are different archives all over the world. And when we want to analyze all this data together, we have to bridge this geographic gap. The architectures used for analysis are also becoming increasingly CPU heavy and IO poor. So we get more and more the CPUs crammed into the same chip. At the same time, the disk technology hasn't substantially changed over the last 15 years. And so we need to rethink the architectures, but it requires quite a holistic approach. We need to rethink also the way we do the analysis and every aspect of this process. And my premise is that the databases are a pretty good starting point because they offer a lot of good features, indexing. So a lot of the patterns that we do in science is, for example, still extract certain ranges of data of large data sets, or we do perform some sort of a select from where type selection of a statistical sample. We reject the obvious erroneous data points and the outliers. So it's a good starting point, but at the same time, we, for example, as we get into larger and larger data sets and more complex data sets, it would be very good to have array support. So, or we want to sometimes do much more complex computations inside the database. So a lot of these things are, for example, driving Mike Stonebreaker to build a SciDB and leading the SciDB effort, where the primary data type is an array. when we look at how most of the data analysis is done today, it's on mid-size Linux clusters, bare-board clusters, typically funded by faculty startups and put into broom closets. So this is not a scenario that is really either sustainable or scalable or maintainable. Universities are starting to hit the power wall. If we need to buy twice as much computing every year, then essentially our electric bills are going to get larger. You know, on the side, the physics building at Johns Hopkins had its transformer burned down about 10 days ago, and for 6 weeks we will be now on 3 trailer trucks running diesel generators, and all the computing is running now at half power. So it already hit us. Yesterday I went to LBF for a few hours, and then there was an electric shortage in the lab. All computers went down. Some of the cosmology simulation data was lost, it turns out. So, soon we are getting to the point when the data stream is so large, like in particle physics already is, that we cannot even hope to store the whole data stream in one go. So radio astronomers are building a prototype for the square kilometer array, the Pathfinder, which will have several terabits of incoming data stream, and the only chance to do anything with it is first to set up a hardware processing of the incoming data stream and only store the outcome of that hardware triggers. And same thing that is done at the LHC today. So what goes? And how long does this data growth continue? And of course, one can argue that in high energy physics we have reached a plateau, because after the LHC, there is not going to be, for 20 years probably, another new accelerator that is going to continue with the exponential data growth. So there the data production rate will remain constant for the next 10 or 15 years, unless they replace the detectors. So the exponential is really coming from the rapidly accelerating generation of inexpensive sensors like the gene chips or the CCD chips that are generated by Moore's law. So one can argue that how many generations of instruments do we have in our respective scientific areas? This is how long we will be faced with this data explosion, except if it wasn't for the fact that software is also becoming an instrument. And the software keeps generating ever-increasing amounts of data, like just larger and larger simulations, and more scientific disciplines are getting into detailed scientific simulations, even systems biology. So this is emerging now, not just in the physical sciences, but in biology as well. So we are creating large and complex simulations. Once we take the pain to take some geographically separated data sets and bring them together and create a new value-added federated one, it makes a whole lot of sense to store it, because the cost of moving the data is probably more than storing it one more time. And then we see also in a bunch of project hierarchical data replication, like CERN creates the tier 0, tier 1, tier 2 hierarchies in the data management systems. So, so in astronomy, just this again, since my day job is in astronomy, the cosmological simulations about 8 years ago have been roughly the state of the art was about 1 billion particles, and they produced about 30 terabytes of data. That is the famous Millennium simulation that went into a tape robot in the Rechenzentrum in Garching. And essentially nothing but the top 1 terabyte has ever been read. Because it was so difficult to get to the tapes, and eventually they created a SQL Server database out of this simulation, and now hundreds of people are using it on a daily basis. But, so it was clear that for the subsequent analysis, again, the database provided a much more convenient framework than the usual case of sharded files over a bunch of machines. But, and this is also the most convenient way to compare to the real data. But now there is a new generation of simulations coming. So there is the Roadrunner at Los Alamos, and the people are there creating the Roadrunner simulation, which will be 1 trillion particles. And so there's a project now at Los Alamos called the Exascale Sky, where these family of simulations each will be about half a petabyte in size. So first of all, it's difficult in Los Alamos even to move it. The Roadrunner is now in the black. So how can you get half a petabyte through their internal firewall? So the guys are thinking about rolling a truck of disks across the firewall because internally everything is choked. They basically archive every packet that goes through the firewall. But even moving then the data, say, from Los Alamos to Hopkins or anywhere, it's quite a non-trivial challenge. So we have been playing with structured data in turbulence simulations. And then again, so today the state of the art is if you want to analyze a simulation remotely. So first of all, the state of the art is if you want to analyze a large simulation, you run your analysis while the simulation is running because you cannot store the output. What if you did something wrong? Then you essentially blew the time. But when the simulations are starting to take 10, 15 million hours on the Jaguar system, you cannot just say, okay, shoot, so let's do it over again. And the other sociological aspect of these very large simulations is that as the simulations are getting larger and larger, a smaller and smaller number of people are able to get to these computers. At the same time, then if only these people are allowed to analyze the output of the simulations, there is increasingly shrinking clientele for these supercomputers, and sooner or later it will lead to the demise of these facilities because nobody will come. Nobody will be able to use the data. So a new paradigm is needed, and we played with an interesting idea at Hopkins, so that instead of moving the large simulation files, which is really impossible, so what if we took basically a large set of large simulations and stored all the time steps that are needed for the analysis, and then we just insert sensors into the simulation through web services. So we insert a whole bunch of particles, and these particles then report back the state of the fluid, or the velocity, or the pressure, or the temperature, or the dissipation rate. And essentially, such a way, by placing the points where we want them, we can get very high resolution output exactly from where we want it without having to move immense amounts of data. And people have been writing papers in Physrev Letters, Journal of Fluid Mechanics on this. So on a typical day, we deliver about 100 million points to the public through this facility. And right now, this is running on an outdated hardware, so we are now moving it over to the Grey Wolf. But in all these scenarios, so I sent out a questionnaire to a bunch of my friends. And what are the biggest needs? And it turns out everybody said I expected everybody complain about I/O rates. No, they don't. That's a secondary concern. The primary concern is they don't have enough disk space to store this data. So like, in real estate, it's location, location, location. Here, I think what seems to be facing in science is disk space, disk space, disk space. And of course, our current problems are nowhere near on the Google scale, so on exabyte scales. So the current problem point is the threshold is about 100 terabytes. So if I have data sets in the 10, 20 terabytes, that's relatively easy. So I just shove a bunch of disks in a disk box to my workstation. If it's 100 terabytes, it already requires more than one server, so you need to start to build a small cluster. Then you need to know what you're doing, how you integrate the different clusters, how you start partitioning your data. So at that point, there are no off-the-shelf solutions. And when it gets to 300 terabytes, it starts to get pretty hard. So secondary is the sequential I/O bandwidths. And what we really need is sequential I/O bandwidths, because if we can only access the data with a random access pattern, then forget it, if it's in 100 terabytes. So the only way to do this at this point, we have to organize the data in such a way that we can maintain a sequential read pattern. So how can we move 100 terabytes within a university? If we had a 1 gigabit per second network, it would take 10 days for the network to run at full speed. So Hopkins, in many locations, it's a pretty advanced university. In many locations, we only have a 100 meg network. So in the building, so on my desktop, I still have 100 megs. Not that I'm not complaining about it every day. In the machine rooms, we have gigabits per second. We do have a 10 gigabits per second backbone, but it goes through firewalls, so which shows the data transfer. And that is the whole campus traffic is going through, including the telecoms, is going through these 10 gig connections. So basically, it would still take a day on this, but only if it was a dedicated 10 gig line. If I put 52 terabyte disks in a 100-pound box, it would take a few hours to move it, except for the copy time. But we have done this on the 10 terabyte scale with the medical school. We tried network transfer several times, and we gave up. And so we moved a bunch of Illumina data over from the medical school just by driving over. In a few hours, I would just plug the disks in, and we were done. Okay, sooner or later, the networks will get faster. Sooner meaning probably on a few-year time scale, and maybe on the wide area on a 5-year time scale. But what do we do but by then our problems will not be 100 terabytes, they will be petabytes. So we can either wait and hope that more slow will be, and the network loss will grow faster, or we try to make trade-offs. And so Stu Feldman gave a really nice talk at Szalay at the conference about high-performance computing, that we call something extreme when we make trade-offs, that we do certain things well and we give up on other things because we trade things for the things which are most important to us. So I try to put together, based upon this, that this is a completely personal perspective. So what I think are the most important issues today for data-intensive scientific computing. It seems total storage, so we need to have, this means that we cannot keep 6 or 10 copies of the data in a ring, in an Amazon ring or whatever. So we need to be satisfied with a relatively low redundancy. Secondary is cost, because we cannot buy an EMC squared type system. Sequential I/O speed, then fast stream processing. If we have finally the data coming up, we can get the data coming fast off the disk, then we also have to catch it and process it. And then then low power has to be there because we are burning down our buildings. And this will be, of course, different in a few years. But also we should look at these. These are quite different, for example, what the priorities for commercial cloud providers. And all the trade-offs they are making makes perfect sense from their perspective, but they are not necessarily the same thing for scientific computing. And the other thing that we see in science is that there is an increased diversification. So one shoe doesn't fit all, and diversity grows naturally whether we like it or not. Why? So we have all these evolutionary pressures. So somebody who has primary large floating point calculations, we see a migration en masse to GPU clusters. So most universities are now, instead of Beowulf clusters, are buying GPU clusters if they want lots of CPU cycles. If we want fast I/O, people are moving to systems where the CPU to I/O rate is much different from the traditional. So this is, I would call, the high Amdahl number clusters. Getting large data means buying lots of cheap disks, not the enterprise disks that all the vendors want to sell you enterprise disks. But for the price of for a single enterprise disk, you can buy five commodity disks. And the failure rates will be higher, we will suffer. However, we can buy a whole lot more storage. Stream processing is emerging. We have to think about how to catch essentially the data streams and directly off the instruments, and what to process, what to sense, and what to store. And we also see a diversification in the software environment. So I made a pitch for databases, but there is now a whole, whereas a few years ago there were a few big database vendors, so SQL Server, DB2, and Oracle. Today we see a whole variety from a bunch of column stores and specialized databases, stream databases, to the regular relational databases and all the NoSQL solutions. And the individual groups, when you talk, this is where every scientific group will want a little bit different subtle specialization. So large systems are clearly more efficient, and there is a large business pressure to kind of build larger and larger homogeneous systems. At the same time, the smaller systems have a lot more agility. And there is also a trust issue on campus or beyond, that do I trust basically a large central organization to handle all my data and all my computing needs, and are they going to provide me with the specialization and the flexibility when I need it? So we built a few years ago the Gray Wolf, so with the help of the Moore Foundation and Microsoft Research, which was an experiment in building out from first principles a very high I/O rate and large disk cluster. So it's a 1 petabyte system. And this is the really important number. So we are able to do 70 gigabytes a second on it, which is very close to the throughput of the fastest supercomputers in the world in terms of I/O, sequential I/O. So the Texas Ranger and the Jaguar all have I/Os, well, at least before the upgrades, they were very close to this number. So the system at this point is pretty much getting full. And so what is the cost of a petabyte? I found this website called backblaze.com. These are guys who they provide basically cloud storage on the web. And they build their own chassis and everything. So they try to do everything dirt cheap. So this was an eye-opening chart. So the cost of raw drives as of August 2009 was about $81,000 for a petabyte. Backblaze, when they add their own chassis and the cheapest motherboards and the SATA multiplexers and so on, SATA expanders, they claim they can build a petabyte with servers for about 117. Dell will sell you a petabyte for about $800K with the enterprise drives and the disk enclosures. Okay, Sun was about $1 million. Now, since it's called Oracle, it's $1.5 million. So Amazon storage would be about $2.8 million to basically buy Amazon storage for 3 years. So they make you buy your storage every month, basically, over and over. And if one buys EMC squared, then that would be roughly the same. So it is clear, as a scientist, if I was given a $1 million or $2 million budget, I would certainly not. Today, I would certainly not do this. So the prices would have to come down dramatically before, I think. And also, there's the issue: how do I get the data into the cloud? So I put in a proposal to the NSF MRI in April about trying to build something, a machine which would go to a little bit to the extremes in these compromises, even more so than the Gray Wolf, since the Gray Wolf was Dell, and it had enterprise disks and so on. So it was sort of a mainstream machine, just put together so that we maximize the I/O. So what if we really went to entirely the cheapest disks? You know, and I always thought, so if I asked Jim that, would you buy enterprise disk or the cheapest disk, he would always have said that buy the cheapest. And so, but the idea is that this would be not kind of a computer cluster, really, but one should look at it as a special purpose instrument. So scientists, as Mark said, they are pushing the edges. And on the edges, so again, we can wait until we can buy exactly the computer that we want from a commercial vendor. But really, if we want to go out on the extreme to the edges, at this point, we have to put much of it together ourselves. And so the system, essentially, the idea is to take about roughly $1.2 million. It will be probably a little bit more, but build a two-tier system where one tier would have just cheap but large data store, about 3 petabytes of data store, and then have another layer consisting of about 90 servers with about 2 petabytes of storage, which would provide a very fast I/O performance. So here, this would provide the redundancy, and then when we move the data to the performance layer, there would be essentially no redundancy, but an all-out speed. And then this would be a combination of GPUs, and the aggregate, we project about a 400 gigabytes per second performance for this cluster. And the idea is that people just bring their large data sets. So I sent this email around Hopkins that, would you be interested in participating in such a project, and what sort of data sets do you have today that you cannot do? I got in about 20 projects or 20 mini proposals with an aggregate data of about 2.8 petabytes. This is just in a single university. And this is the distribution of the problem sets. So it peaks around between 80 and 160 terabytes. So this confirms that people when people try to think big, now today they think about 100 terabytes, basically. That this is at the limit of their perception, with a few exceptions. So we tried to solve the power problems in building just a bunch of low-power motherboards with solid-state disks. So to see that what can be built from that runs still on a single wall socket. And combining SSDs with a few hard disks, I don't want to dwell too much on this, but we were able to build a little cluster for about 30 grand that was running, that has a sequential I/O of 18 gigabytes a second. And we were able to do some pretty interesting data mining, 6.4 billion tree traversals over more than a terabyte in 5 minutes. So this is a possible way to go, but right now this is too homegrown. So how do we bring in GPUs? These motherboards had some GPUs built in, but it is right now very attractive for the guys who are doing the high-end computations. But how do we integrate it with the data-intensive computations? How do we feed the data? How can we run it how can we integrate it with SQL Server? So we set out an extension to SQL Server where the GPU card sits in the same server, or it can actually sit somewhere else, but the bandwidth is higher if it's in the same server. And we have the C# .NET layer talking to SQL Server. And between the two, we had to set up an IPC layer in order to have the thread control run by the operating system and not by the database. So there was too much mismatch between the two. So otherwise, the threads always froze. So just very quickly, so basically what we have to do is that the IPC loads a DLL. The DLL contains some wrapper code that can run on the CUDA end. And it also contains a method that can execute a SQL statement that pulls the data into the IPC buffer and then hands the pointers to CUDA. And we can write things. This is basically a stored procedure that runs the Swiss Waterman Goto algorithm on a large sequence data set, and about 100 times faster than on a Pentium. And it's out of SQL Server, and the result is stored in the database. And another demo is that of a galaxy correlation function. This was done on a SQL Server workstation, running SQL Server, and not even a very high-end card. And Tamás Budovári wrote this code. And we were running about 600 trillion galaxy random pair computations in about a week period, in a period of a week. And this is all wrapped into a user-defined function this time, which again automatically, which just says pair counts. And then here we send the different queries that fetch the data into the, so this is the query string that we give it to the function, and that is sent to the IPC layer, pulls in the data, computes the pair count, sends the results back. So this just shows basically the two-dimensional correlation function. This bump here is the acoustic resonance of the universe when it was 300 million years old. But this figure contains essentially 600 trillion galaxy pairs computed within the database on a single hardware. And the last bit is that we were interested in, are the arrays really kind of a SciDB only thing? And László Dobos, who is a graduate student in Hungary, but spent last summer with the SQL Server group as an intern. So in about 3 months, he built a SQL array native data type, or not native, it's a user-defined data type, where we use the blobs, the var binary maxes. But for example, we can do pretty fancy things in SQL. So this is just a simple code example. A is a large array of doubles, say with 3 indices like coordinates, x, y, z, or 3 velocity components. So it's a single homogeneous blob, and what I want is to take little 4x4 subcubes out of this, average the 3 vector components, and store this in a new array. So collapse the array by a factor of 4 in each linear dimension. So the way I would do this is that I call the split function on the array, and say that I would like to, this is the kernel, the splitting kernel, so I would want to create a 4x4x4 subset. So this extracts all the little subcubes of this array, stores puts it into the select of the function. So this is the subcube, and then I run an average function, an aggregate function on it, and pack it into a table. Then I take this table and concat it back into an array. So basically, this would have taken quite a few hundred lines of C code or C++ code. So summary, large data sets are here today, but off-the-shelf solutions are still not. So we are still on our own. If I look at around nationally, there are still no real data-intensive computing facilities available. Slowly, the high-performance computing guys are also realizing that they are choking on I/O. So there is a hope for a communication or a conversation. Cloud hosting today, no matter how attractive it is in the long run, it is still very expensive, and there is quite a large difference between the trade-offs. Scientists are frugal, but we are also pushing the limit. We try to stay on the edge, so we are building our own. I think we start to see campus-level aggregation simply because there is no other way. Individual groups cannot live in this world any longer. And what I think is going to emerge is campus-level aggregations will be the gateways to a future science cloud whenever it is emerging and we find the right business model. And we are creating, and there is an increasing diversification emerging, but always out of commodity parts. So the cheapest graphics cards, the cheapest disks, and systems and SSDs are also entering this picture in a big way. So I think what we will see that we will be able to migrate more and more of the high-end data-intensive computing still around databases. Thank you.
So we have time for a couple quick questions.
Fantastic, as always, Alex. Over the last 10 years at Southampton, we've moved to completely centralized HPC. We have an 8,000 core machine where we used to have immense diversification in our HPC in different departments. We're looking at storage now, and it's our central IT group. How do I buy this off the shelf? I mean, are the Backblaze guys reasonable, or, in terms of...
They don't sell.
Right.
But they provide a recipe.
So if I have $1 million to spend and I want to go this approach, what's your advice?
Well, so we are going basically super micro chassis and otherwise enterprise and commodity disks. And right now, so we got the NSF grant actually. So right now, until about January, we are building prototypes and doing benchmarking the hell out of everything. And experimenting with different disk controllers, a few different motherboards, and a few different chassis.
When you go production, is your central IT group supporting the production facility?
Yeah, but it will be, so this is why we call it an instrument. So what I envisage is that there would be, basically people bring their data, probably driving the disks to our building. Then they can get like a 6 months allocation of a bunch of servers. Or they can form maybe a larger collaboration. And some of the servers will run Hadoop, others will be running SQL Server, yet another bunch will be probably running plain bare iron Linux. Whatever is needed to get the best science out of this 100 terabyte.
And how many people does that require? Dedicated people to support that?
I think probably 2 or 3.
Okay.
2 or 3,
That's
maybe
great.
2. So I'm thinking about roughly 2 in the system support and DBAs, and probably at least one other person who would be an application support, who, for example, understands CUDA and can help deport some of these applications. But here the idea is that every machine would have the PCI slots would be split between disk controllers, GPUs, and the fast network card.
Okay.
So it's all about kind of I/O and crosstalk.
Thank you.
So,
great talk. Could some of these problems be alleviated by coming up with better algorithms that would filter the data, or is it the case that in your field you never throw away anything?
Yeah, okay, it's a very good question. So in a way, I think, yes, definitely we will. There is a whole algorithmic aspect about this, and smarter and cleverer algorithms which scale better that I didn't talk about. There is also, by the way, an interesting approach emerging called compressive sensing today, that in order, if I take a 10 megapixel JPEG image, I can compress it probably to a few hundred kilobytes. So in a way, taking the 10 megapixels is very redundant and wasteful in a way when the information is only 100 kilobytes. So in a scientific experiments, could we design our sensors in a smarter way that we take the relevant parts of the data that contains the information and not take the fluff? So, and there is now some of the world's most famous mathematicians like Terence Tao and others are working on this right now. But for now, we are stuck with taking the raw data as it comes off the sensors. And I haven't seen a scientist who would be willing to throw it away unless it was external conditions forced it. So I think like PennSTARRS is an astronomy project in Hawaii, and soon they will hit the point when they cannot. Right now they still store all the data that they are taking, but pretty soon they will have to go into a revolving scratch buffer mode, where they will have to start to throw away the older data. So,
thank you.
We'll have to do it afterwards because we're running late. So I want to. Both Mark and Alex will available afterwards. But we need to move on to the next session. Thanks both to Mark and Alex.